Okay, well, let's just go. All right, so originally this talk was Semaphore roadmap in Ethereum, but I had to commit to the title of the talk a long time ago, and I should have hedged my bets and put this other subtitle here to be able to talk about something else if I wanted to, because I'm gonna talk about Semaphore, but I'm also gonna talk about some other stuff. So, okay, so first of all, I'm going to talk about Semaphore and how we can use it to make generic privacy applications. So at the moment, Zcash have this really cool circuit that you can use to make anonymous transactions. And this is really interesting, but we can also use the same system to do other things. So this is what we've been working on in Ethereum. And I'll talk about that a little bit. And I might talk about identity systems. And then I'll talk about collusion-resistant voting. So hopefully I'll try and keep the voting theme going and show different problems and different solutions as we go along. Okay. Cool. Okay, so just like a quick introduction to how these things kind of fit together. So basically, when we want to do privacy things, what we do is we make a Merkle tree, and each leaf in the Merkle tree, A, I, D, C, and D, are like a public key. Yeah, and each public key is associated with a private key. And in order to make a proof, you need to have the private key. So only the person who knows the private key is able to make proofs, right? So the interesting thing is that if we put this inside a snark, we're able to make proofs without revealing who made the proof. So this is just my kind of abstraction that I use for the snark stuff. And if you went to Elena's talk yesterday, I think she used the same abstraction. So basically what we do is we say, okay, we have this zero knowledge proof that we can basically put some kind of arbitrary computation inside. And then we have some inputs and we have some outputs. So you give certain inputs to the proof. The proof is, you make a proof of what is defined in here. Where's my laser? There. Yeah, so we put like arbitrary code in here, and then you get a proof that gives you like the result. Okay, so we already know how to define like the code in here, and I'm not going to go so deep into how we do that. But just to give you like a rough overview is that we prove membership of this Merkle tree, we validate a signature, and then we give some outputs, right? We say that, we have to give the Merkle root as an output because that kind of binds you to the group that you're talking about. And then we have to make like this kind of clever nullifier on the other side. Instead of just having a regular nullifier, we want to have a nullifier that's different if you use a different signal. So we have this different kind of external nullifier, and we hash it together with the actual ID commitment or the nullifier in the original system. Okay? Okay, so we can use this for a whole bunch of things. One thing, and it feels like the most basic thing we can do with this, and the most kind of low complexity thing that we can do, and something that's like really important to do is to make a mixer on Ethereum. So about this time last year, we were at ZCon 0, and there was this really cool talk by Mary Maller, and it was by this group who did like an empirical analysis of the Zcash. What's my laser? Of the Zcash blockchain. So basically what they found was that there was a bunch, like although it's like private what's going on inside each transaction, there was all these heuristics that you could use in order to find out who was doing what. So okay, let me explain one of the heuristics and then I'll talk about it. So one of the heuristics is this. Okay, so this picture is kind of how things worked, and I took this from their slides. So basically, you have like the transparent address outside this kind of shield, this kind of cloud. And when you go inside the cloud, you go into the shielded pool, and then on the outside is more transparent addresses. And it turns out that people used to deposit directly into the shielded pool, and then immediately after withdraw from it. So there's this like kind of, it's very clear who that is, right? If someone deposits 1 second and then the next second they withdraw again, it's obvious who it is. Another problem is that if you have the same balance, you deposit that balance, and if it's like an unusual balance, it's easy to kind of link it to a deposit, right? So, okay, so this kind of affected the way that Zcash was working, or Zcash were kind of thinking about their privacy. So what Zcash, and like it kind of undermined a little bit of the guarantees that people thought that they had. So Zcash's reaction to this, like generally, I don't know if someone disagrees with me on this, but was to say, okay, let's just move everything inside the privacy pool, inside the private pool, and we'll just have private transactions all the time, privacy by default, and then these heuristics won't really apply, or they won't be as severe. Yeah. So we can't really do this on ETH, right? Because Ethereum seems to have like different priorities to Zcash. Like Zcash says that, okay, we should have privacy as our basic thing, or the main thing that they're trying to optimize for. But with Ethereum, because we have these smart contracts, and it feels like scalability is more of a priority there. So feels like that's more of a priority there. So sorry, one sec. And also, it's actually really difficult to have general smart contracts and privacy at the same time. Because if you have general smart contracts, you have to have this kind of global state, yeah? And if you don't have global state, you have to have this global state, and the point is someone has to know the global state in order to do smart contract things, right? If you don't have like if you want to do some kind of batch auction exchange, you have to have a public numbers that people are able to interact with. And if you try and do these smart contract things with Zcash, you would end up leaking information. So there's a solutions to this. You can do things like MPC, but that kind of degrades the privacy that you get. That kind of degrades the privacy you get, because instead of having, like, the current situation with Zcash is everything is private. And no matter what happens, everything is private unless you show someone your information. But if you do MPC, you can have we can make fault tolerant MPCs, but the 66% of the MPC is able to collude in order to reveal private information. So that's kind of something that we could do with Ethereum in order to have this kind of general privacy, but the guarantees are not really as strong. And yeah, they're not really as strong, and it's really useful to have this global state. So let's try and come up with something else that we can do that's not this kind of crazy MPC, but is also something that's still kind of useful and gives us kind of some kind of decent privacy. Yeah, so the idea is to make just a very basic mixer, right? Where the mixer accepts one kind of volume and one kind of, so it'll accept like 1 Ether. You deposit 1 Ether and you can draw 1 Ether, and we kind of lean very heavily on the user interface here to sort of prevent people from falling victim to these heuristics that the previous paper found. So yeah, so this is roughly what we're thinking, and hopefully we'll be able to make this kind of. I think that the privacy you get here is not as good as Zcash, but what you can do is it's kind of opt-in, right? So you can deposit into the pool, and it forces you to wait a certain amount of time before you withdraw. But if you don't, if you you can totally bypass the user interface and just withdraw, but that kind of hurts your privacy. And you can also deposit and wait a very long time and then withdraw, and you still get kind of roughly, you get kind of better privacy properties. But anyway, this is kind of the rough idea of some, the most basic mixer that we can make, and hopefully people will be able to have anonymous gas with this. Yeah? Okay. Yeah, so then another problem is who pays for the gas. So Ethereum has this gas model. So someone needs to come forward and pay for the gas. And yeah, so there's all these different ways to solve this, but I'm kind of a little bit low on time, I think. So let me skip this part. And so anyway, so what we do is that whenever someone withdraws, we pay 1% of the withdrawal fee to the miner or to the person who broadcasted that transaction. Yeah, so we just have to come up with a decentralized way for people to advertise this service. Okay, so up until now I just talked about using snarks for transactional privacy and for mixing, but then there's a whole bunch of other interesting things that we can do that's not just money going in and money coming out. That's not just transactions. That's also really super interesting. So one thing is, and I think I'll talk about a little bit more about the first one, the journalists having these anonymous sources that are all part of the same group. Another one is to make an anonymous DAO where you can use so people are part of the DAO and you know who they are, but you don't know what they're voting for or what they're proposing. And then token mixer, I've already talked about it. And then we could also do something like anonymous universal login. And the cool thing is that we can use the same circuit that we're using for the mixer for all of these things, right? So the mixer is just like the first step and the first kind of most basic thing that we can make. And hopefully after we do the mixer, we'll start to do these other things. So let me give you an example of the journalist application. Okay, so we have this journalist, right? And this journalist has a bunch of sources, and all the sources, and the sources don't trust the journalist, but they also want to give like a quote to the journalist or some information. But the journalist can't accept the quote unless she knows that they're part of this group, right? So what happens is the journalist goes around to all of the group and convinces them to join this Merkle tree. Yeah, so each of them gives each of these people gives her a public key, and she puts them into this root, into this Merkle tree, and puts it in a blockchain, and convinces and then they all go kind of out of bound and make sure that they all are part of this group. And then, okay, oh yeah. So she knows that they're all part of this group. So now each of these people is able to make a snark to prove that they're a member of this group, and they're able to like attach a message to it. So the message could be like like a quote or some information that they want to share with the journalist. And there's no way for the journalist to find out who gave her the information unless all of the members of the group collude. There's like some attacks that the journalist can do here to kind of trap one of the sources, but that's I can talk about that later if people are interested in chatting about it. But this is just like a sample application that we can make with the same circuit that we've done before. So we don't have to do the ZK snark overhead for a bunch of different things. Yeah. Okay, so so the next idea, and this is where the talk kind of diverges to between what I had planned when I proposed the talk and what has happened since. So since then we came up with this proposal to do, Vitalik came up with this proposal to do coercion-resistant voting. So basically the problem is that if people are able to vote, and they get like a receipt for voting, they can be bribed, right? So if someone and like if we do this on a blockchain, it can be really difficult because you can pay people to bribe, and you can do this really efficiently and trustlessly. So people can bribe other people, and it's a big problem. So we don't want users to be able to be bribed, and even if the user is like coordinating with the briber, even if the user is like, I really want to get a bribe, I'm going to work with you so I can have a bribe. So it must be impossible to prove how somebody voted. That's the only way to come up with this. Even if the user is colluding, it must be impossible for them to prove that to someone else. Right. So this is a project that we worked on at IC3, MACI, Minimal Anti-Collusion Infrastructure. So basically what happens is we have this operator, right? And the role of the operator is that they're able to they're the person who's supposed to count the votes, and we're happy with we're not happy with it, but we accept that the operator is able to bribe people, but we can't accept that they're able to bribe people, but we can't accept that they're able to sorry, one sec. We can't accept that they're able to like arbitrarily change the result of a vote, but I mean they could just kind of disappear and refuse to release the result of a vote, and that kind of sucks. But we could just rerun our vote again and kind of slash them, hopefully. Okay, so here's how it works. So we have our users, and they're all in this Merkle tree root. And what we do is all of the users create their votes, right? They encrypt their vote. So they create a signature that says, I want to vote this way. Yeah, sorry, let me start again. So there's two kind of commands that the users can make. The command number one is that they can update their public key. Yeah, they're all part of this group on the right here who are able to vote. And anyone who has the current public key of a leaf is able to say, okay, I want to change my public key and update it to a new public key. The second thing they can do is they can vote. So they can kind of update their vote and say, I want to vote this way. So what happens is that everyone who wants to vote creates their signature and then encrypts it for the operator and publishes this on a smart contract. Yeah. Then the operator is forced to go through this list in the smart contract one by one and process each of the votes. So what they do, so what happens in the snark is that they validate the signature and they check that that's the current signature of the leaf in the tree, and then if that's correct, they update either the public key or the vote depending on what the user wants. Yeah, they update the state based upon the commands. Okay, I've already talked about this one. Okay, so what do we have here? To just slow down a little bit because maybe this is difficult to understand. So So now we have a system where people are able to come forward. Let's do a sample bribe. Okay? So let's say that I have the key of A and I want to convince someone that I voted a certain way. So what I can do is I can show to the briber the signature that I had, as well as the encrypted format, and they can re-encrypt it and see that, oh yeah, this is in fact what they voted for here. Yeah, but the operator can never be sure. The operator can never be sure if I had already executed that command before or not. Yeah. Yeah. Okay, so this actually helps a little bit here. So the way things go is we have this list of commands, and the operator is supposed to process these commands one by one. Yeah. So, but some of these people we assume are malicious, and some of these people have like revealed their encrypted text to an operator in order to get a bribe. But and what's happening here is that we have our list, but we just have a single. This is just a single person. Yeah, a single vote. So if this person reveals this to the operator, to the briber, then the briber is fully convinced that they voted a certain way, because they know the state of the system before, and they know the only input to the system. Therefore, they can calculate the final state of the system, right? Because they just execute this one state. But if we add a second person, yeah, so now there's two people. So, and the second person here wants to get bribed. So they reveal their encrypted text. They reveal their decrypted text to the briber, and the briber does the encryption and says, "Oh, this equals this. Yes, everything is okay." So then, but the briber can't be convinced by this, right? Because the user could have at index 0 updated their public key to another public key, and therefore command 1 would not work, or they could later on create another vote that is processed. Yeah, to undo the transition that they showed to the briber. So it becomes difficult or impossible for a briber to be convinced that someone else is being because the briber basically needs to know all of the commands that have happened in order to accept a bribe. And as long as people are honest, as long as some people are honest, there's no way for them to be convinced of this. But the first person can get bribed, but we can have this kind of key update system where people update their keys before they actually vote, and that should work fine. Okay, so here's some attacks, right? So one kind of attack that you can do is you can put your key into trusted hardware, and the trusted hardware works in such a way that only if the briber says you can vote this way, can you vote this way, and then they're convinced that you voted a certain way because they know you can't vote another way. And a similar attack is to do the same thing with an MPC. So instead of putting it inside trusted hardware, you put it inside an MPC. Yeah. So some solutions to these attacks is to force every user to produce like a proof of work that proves that their key material was not inside trusted hardware at a certain time. So basically, you come up with this kind of proof of work that you force all the users to do, and if they don't do it, you force all the users to do, and then you use the snark to prove that they did the proof of work, and you assume that because they did this proof of work that was designed to be difficult to do inside trusted hardware and inside MPC, that it worked out, that their key was available then, right? But then there's a whole bunch of malicious operator attacks. The operator can still bribe people, and the operator can still refuse to release the result of a vote, and that's a bit of a pain. So what we can do instead, so I think like long term we'll try and make the operator into an NPC. So then like 66% of the NPC would need to collude in order to get 66% of the NPC would need to collude in order to bribe someone. So that's kind of the longer term plan. Yeah. Okay. So that's my time. I mean I have some more time, so we can have some questions if people have them. But there's more. I mean here's a nice write up of the NPC, or of the coercion resistant voting, and here's some code for different things. Oh, so as well, just to say that the mixer was joint work with Kobe and with Ouija, and the Semaphore circuit was joint work with Kobe. Yeah. So thanks to them for their help and contributions. Yeah. Thank you.
Hi, thank you. I just had a question about when you talked about the anti-collusion in voting, does that also include, like, let's say, for example, that you're one of the people that are supposed to vote, you're sitting in front of your computer,
Yeah.
and I'm the briber, and I'm standing behind you, and I'm looking at what you're doing at the screen, and you show me, like, I can vote for this value or that value, and
Okay.
does your scheme include collusion resistance at the in person in real life scenario as well? Thank you.
Okay, so the person who in that situation, the person who's bribing you, needs to be convinced that you didn't update your public key before, and that after they leave, you don't undo your vote, right?
So can they keep you in a cage afterwards?
They can keep you in a cage afterwards, but they also have to keep you in a cage before.
Okay.
They have to kidnap you for the entire voting period.
Thank you.
Or they need to deprive you of your key afterwards.
All right, I'll keep that in mind.
Yeah, but this is kind of the case anyway, right? Could you kidnap someone and force them to vote a certain way? Maybe not. We could do like a public vote if this is a problem, and then maybe this attack doesn't work, or at least it forces you to abstain.
Hey, so I was curious about the mixnet you discussed, but briefly. So maybe I'm confused, but I'm envisioning something where you make a transaction that puts something into this Merkle tree that's on chain. I'm not sure what's on chain.
That's exactly it. Yeah.
And then another transaction takes it out of this Merkle tree, right? And so your anonymity set is in the Merkle tree?
Okay, so you deposit into the tree, but then when you withdraw, you don't withdraw the leaf, because if you did, you could see that leaf being updated. So what you do is you generate a nullifier. Yeah, and this nullifier is like deterministically generated and unique to the leaf. So you can't do a double spend because the nullifier is already. So whenever you do a spend, you check that the nullifier has not already been spent. Yeah.
Okay, so you have a separate nullifier tree that's off-chain.
No, it's on-chain. It's in the
Also
smart contract. Yeah, so this is a problem. I mean, the state of the contract kind of grows, and you have to, it just gets bigger and bigger.
Okay, but in any case, like, you're not actually like anonymizing your ETH because the transactions you make are still in clear text on the network. You're just getting some like secondary token which you can pretend to be inside some anonymity set.
No, you are anonymizing your ETH because you deposit the Ether in and you withdraw it to a new account, but the withdrawal doesn't use any of your doesn't use your gas. There's like this transaction relayer market.
So it's in one TX.
Yes. Oh, it's in two transactions: the deposit and then the withdrawal.
But so the secondary withdrawal goes to a second TX. But I can look at the TX from whoever put in the TX that makes the withdrawal. No,
you can't, because you can't link the deposit to a withdrawal because the nullifier is hidden at the deposit time. Yeah.
Okay. Yeah? I see what you're saying.
Yeah. Yeah, so this is kind of a key problem, right? That we want to have the deposit and the withdrawal, and we want to try and have the longest period possible between the two. And ideally, we'd have like the biggest anonymity set as well. Yeah. So this is kind of like trade-offs that we're trying to solve. Yeah. Cool. Thank you.
Thanks for the talk. It seems like in the last construction, you need some sort of a trusted operator to manage this. I'm curious if there are any schemes where you can do totally decentralized. Sorry, I'm blanking on like what the protocol for the last thing was, but
yeah. So one thing we can do is have an NPC.
Yeah.
Yeah. So the NPC would reduce it to like 66% of a group would need to do it. Another thing we can do if we can do
maybe
like
secret sharing.
Sorry.
Could use like some sort of secret sharing scheme to do receipt-free voting.
Possibly. I think the other schemes that are available depend upon some kind of more advanced crypto that we don't have available in the EVM at the moment.
Okay.
So I think with homomorphic encryption you can do something, but I'm